So hello, welcome to this morning's SeptembRSE session. Just to remind you, the session is going to be recorded and uploaded to YouTube. So we have two events this morning. We have first up Alberto and Francesco from the Politecnico di Milano, who are going to be doing the walkthrough, taking the ninja out of using GPUs, introducing the latest updates in the GrCUDA polyglot CUDA API. We'll then be taking a short break, and then we'll be moving on to a panel where we'll be exploring the RSE role in HPC, AI, and ML in emerging and unconventional fields. So without further ado, I'm just going to pass straight over to Alberto and Francesco for what I think will be a very enjoyable walkthrough. Off you go.
Thank you. So let me see if I can share my screen, then I'll begin the presentation. All right, I think that everything should be set up. All right, so I'm Alberto Parravicini, PhD student at Politecnico di Milano, and I'll be presenting a short introduction to the GrCUDA API with a focus especially on its latest updates. Then I leave the stage to my colleague Francesco, who's going to show a very wonderful demo of this work, along also with exploring the code if you want to understand it better and play with it yourself. So the starting point of this research is that GPUs these days are really powerful for anything related to parallel computing, from deep learning to image processing and even database workloads in some cases. But as it turns out, they're still very difficult to use. And it's not just about programming the GPU themselves, because of course you need to understand very well the underlying GPU architecture, but it is also a problem of writing the host code, which is the CPU code, which handles things like GPU scheduling, data transfer, synchronizations, and so on. And finally, GPU is difficult to integrate with higher level languages. For example, if you want to provide GPU acceleration to your Node web server or your Python scripts, and so on. And that's because you don't have access to the same features and optimizations of the lower level C++ API. And overall, it really takes years to become a good GPU programmer. In this work, we are specifically targeting the last two challenges so that you can actually spend more time doing the actual GPU programming without having to worry about everything else. To give you a better feeling of what these challenges are about, here we have a somewhat small snippet of GPU host code. So this is not the actual GPU code, but it is a CPU code which handles data allocation, data transfer, scheduling, synchronization, and so on. And as you can see, for just 3 GPU functions, there's a lot of extra code which is required. And what's even worse is that a single mistake, for example, if you forget to synchronize some computation, will most likely break your entire application. What we would like instead is something like this, where you have the same syntax for CPU and GPU functions, and everything is just much simpler. Even better, like functions that operate on different data to run in parallel, because there's no reason why they should wait for each other. And you also want this to work not just with Python, as in this example, but also with any other languages, such as Scala, JavaScript, R, and that's why the GrCUDA API was built. It is a polyglot CUDA API built on top of GraalVM, which is a polyglot JVM, which is able to run not just Java, but also Python, JavaScript, and many more languages. And basically, GrCUDA can provide GPU features to all of them. And it does so through a single backend, so that we have exactly the same API and feature as each language. GrCUDA is now developed by us at NextLab with the help of Oracle, and I also wanted to say that it is completely open, so you can just download it at this link. So here we can see some small examples of how it works. We have a small functions where we are simply adding 1 to all the values of a vector. And here we can see, for example, how we can build and compile these functions. And you see how that's not something we have to do before running the code, but we can do it directly with our script. Then here we see how we can basically initialize some data that we are going to provide to the GPU. And basically you see that, again, it is really very simple. And in the end, we can just call our function. And once again, it's very simple. And you can also see how basically if you want to do the same thing like in Python or R, it is exactly the same API. So overall, the main strength of GrCUDA is that it really offers much better productivity. It is not domain specific, so it's not just, for example, for image processing, but you can use it for any kind of CUDA computation. And we already have support for libraries such as QBLAS, QML, and more. You don't have to worry about managing data because that's also something we can do for you. And you don't have to worry about compiling the code before running it. Also, which is very important, we have a single backend. So basically, every new feature will be available to all the languages, basically without having to keep track of many different APIs. In our demo, you will see how the GPU host code is about 8 times shorter than the corresponding code written with the C++ API. And it is basically just much simpler. And now we actually provide even better performance because we now offer transparent optimizations for the GPU scheduling. Basically, the idea is that we are able to overlap, for example, GPU computations on different data, CPU and GPU computations, and also data transfer with a computations. And that's actually something completely transparent, so you don't have to specify by hand any kind of data dependency, and you don't have to change your code. You can just take your existing GrCUDA code, and basically you will get better performance. Basically, we will see in the demo and also in our paper how, thanks to all these optimizations, it is possible to get often more than 40% better performance. And what's also very nice is that we are basically able to offer the same performance as end-optimized code written with the low-level C++ API. So we are really able to offer great performance with much simpler code. And for now, that's all. I leave you to the demo. Thank you.
Okay, so now let me share my screen so we can begin for the demo. Okay, so first of all, thank you, Alberto, for this introduction, and I would like to thank you all for being here at this demo that showcases some of the capabilities of GrCUDA in a specific setting. So first of all, what is this specific setting? Here, we want to create an image pipeline such that it gives a retro look to all of your photos. A thing that you, of course, do not know about me is that I am extremely passionate about film photography. And the thing that bothers me the most is when you take, for instance, a picture with your cell phone, with your smartphone, a digital picture, of course, and you want to give a retro look, but some of the times all the filters that do exist just change the colors of the image. So they don't change the grain of the image, the actual feel of the image. So since I'm a computer scientist, the most proper way to achieve my goal is in a completely over-engineered way. So, and this is exactly what we did. And here's a little overview of the full computational pipeline that we do in order to give your images a retro look and feel. And we'll see that with a little example of this extremely famous photo of Lieutenant Collins for the space shuttle mission. And the first thing is that we, of course, we want to create some out of focus background. So we apply a blurring filter to the whole photo. And then since we want to also make the subject pop up with respect to the out of focus background, we also apply a sharpening filter to the photo itself. And those two things are done basically in a separate way. After both filters have completed, we compose the image. We add basically the contribution of the out of focus background and the enhance the sharpened image into a single image, which now, as you might see, more clear edges and more out of focus background. And finally, we actually apply the filter to the image. So this is all fine and dandy, but let's see that in practice. So here we have our little demo, which is set up on to work on OCI, Oracle Cloud Infrastructure. As Alberto was mentioning before, all of the code is fully open source, and you can browse it at the link that Alberto has given. So we provide also scripts to actually run, to actually install all the dependencies and actually run these this exact demo in our repository. So the backend is starting here, and you've seen that this is a little bonus. We are using, of course, GPUs. And let's see. Let's go to the actual website. Sorry, I have the Zoom things here. So localhost. So here we are. So this is the website that showcases our actual demo. It starts with a brief introduction of what each scheduler actually does. So as Alberto was mentioning before, we have different schedulers, the synchronous and the asynchronous scheduler. When the synchronous scheduler performs all the filters one after the other, whereas the asynchronous scheduler, as you might have seen already by this picture, performs the kernel, which can be performed in parallel, which basically means that they have no data dependency between one another, and everything is performed in parallel. Also, we provide another version of this image pipeline, which is the native CUDA version, and this is done in order to actually test what are the execution time of one pipeline instead of the other. So let's see how is the actual computation performed. So I will start the computation, and you will see in the top right corner that we have a little progress bar that shows you how many, what is the percentage of images that are that have been already computed. And let me show you just a few images here. So here we have the actual image that has been to which a retro filter has been applied, and everything can be downloaded to the user if it's necessary. So another interesting thing that we have created here is the race mode, in which all the three separate, let's say the two separate scheduling criterion and the CUDA native binary are run one against the other to see which one finishes the earliest. And as you can see, the whole computation has started, and of course the user can take a look at each image whenever it wants. So the actual fact that the computation has not finished does not hinder the possibility of the user of just downloading the images. And here we can see that after the computation ends, we also have the execution time for the 30 images that we have here. And as you might see in this example, the performance of the asynchronous scheduler are pretty close to the performance of the native binary, and actually just a little faster due to the fact that there is some overhead in actually spinning the C++ binary and the computation each time. In any case, it is much faster than the synchronous scheduler. So let's go back to the actual presentation, and let me show you how everything does work. So as you might have seen, we have different sections here. And the first one that the user sees is the front end, which basically showcases the different computation modes. So either synchronous scheduling, asynchronous scheduling, or the native computation. When the user has selected via the Start Computation button the actual method of computation, everything is passed to the backend, which sets up the pipeline inputs. So basically reads the images from the database and does some little pre-processing, for instance, some scaling of the images, and creates the buffer, which will be used by the GrCUDA kernels. After that, the actual GrCUDA backend launches the image pipeline, and in this setting we have opted to choose to launch the pipeline on different GPUs on separate backends in order to better capture the execution time of each specific pipeline. Whereas if we were to run everything on a single GPU, of course it would have worked, but in some case we would have got some not so consistent timing due to how the internal scheduling policies of the GPU works. Everything, of course, as I've said before, is run on Oracle Cloud Infrastructure, and we are using the shape VMGPU 3.4, which has 4 GPUs. So let's actually dig deeper into how everything works, starting from the front end. So first of all, the user can select the type of computation, synchronous, asynchronous, or CUDA native, or the race mode if everything wants to be run at the same time. Then it starts the computation via the button at top right, and it communicates the policy to the actual backend. And after the computation is finished, everything is passed forward to the front end, which displays the final images either in a thumbnail form or in the full resolution form, which is the one when you click on it. And everything is handled completely asynchronously via WebSockets, which basically means that the user cannot, the user can still interact with the website while the computation is being performed, and can still interact with the images and actually load them. So let's take a look at the actual code for the front end. And here I will just show you the JavaScript code that is actually in charge of connecting and handling all the images, and not the HTML code. Otherwise, this presentation would be approximately 6 hours long. And the main thing that we can see here is that here we take use of basically a native JavaScript object to create different WebSockets and attach those WebSockets to different ports in the backend. And this is for the reason that I have explained to you before. We have separate backends that interact with separate GPUs running on separate processes, of course, and on separate ports in order to better capture the execution time. After the connection has been performed, the next interesting thing is the fact that when you click on the begin computation button, the computation actually starts. So this is just a case of sending an init message to the actual backend. For the case that it is not race mode, we just select the proper backend to send the init message. And for the case for the race mode, we just send the begin computation message to all of 3 WebSockets at the same time, and then we can receive the messages from all those 3 backends simultaneously. I've talked about messages, so what are the messages that we are receiving? Basically, there are 3 kinds of messages. Sorry. The first one is, of course, the handler for the execution time that you have seen in the race mode, and this is just a message that gets launched from the backend when the computation is finished and gets added really simply to the front end. The second message type is the actual event that the image has been processed, and here we just straight up add it to the image gallery that you have seen, and we enable the user, we give the user the possibility to click on the image and then open it in full resolution. The last message is actually the one that involves the progress inside the progress bar. The backend continuously sends the message related to how many images have been performed with respect to the whole set of images. So we can give the user an instant feedback on how long is it taking and how much time does it need to be waiting in order to have the full computation done. So here we have finished with the front end, and let's continue actually with the analysis of the other 2 pieces of this. The other 2 pieces of this demo. The second thing, after the front end has sent the message, everything is passed to the backend, which of course receives the init signal and dispatches the appropriate backend in the proper way to which it is configured. So if the synchronous backend is required, then it dispatches the synchronous backend, the native backend, or the asynchronous backend, and so on. Of course, everything is completely hidden. The type of backend which is chosen is completely hidden to the Node.js backend, and everything is passed through a proxy in order to abstract the fact that the backend is interacting with different kinds of computation. Of course, the backend is also in charge of handling the actual read and write of images, and so it does that. It creates also the proper buffer for the computation, and is in charge of also alerting the front end when the computation of the images has been finalized. So let's see the code for the beginning of the front end. Initially, the number of GPU, the actual which GPU needs to be used in the computation gets passed via a command line argument to the backend, and when the front end actually creates a connection, we create an instance of this object which is called GrCUDA proxy, which is in charge of actually proxying the computation for the 3 kinds of computation that we have, and send them via a unified interface to the actual front end. When the front end sends the begin computation message, everything is passed forward to this function, which is called appropriately named begin computation, which is basically just in charge. You can see, as you can see here, you have basically just a normal switch case, and it's in charge of dispatching the actual GrCUDA backend. A thing that you might notice is that for the case of computation of the computation using the synchronous scheduler and the asynchronous scheduler, so basically we are calling just the same function, and this is due to the fact that the option of using an asynchronous or synchronous scheduler has to be passed via a command line argument to the Node.js binary in GraalVM. So here the main thing that you can see is that you have we don't have any single line of code which is different, and we obtain way better performance, as you might recall from the initial race mode. So let's take a look at the run GrCUDA function, and this function is basically just in charge of looping through all the images that we have here. For this demo, we just use 30 images, but of course we can support an arbitrary number of images. It's just for keeping the execution time lower. And when the images has been selected, everything is passed forward to this GrCUDA inner function, which is in charge of actually performing the whole bulk of the computation. So first of all, we have the image name, the actual identifier of the image, and we can load the image, as you can see here, using the OpenCV bindings for Node.js. And so and this is in charge of basically creating a matrix from the image and then returning everything to the actual front end. After the image has been loaded, we have this either process image black or white and process image color, which is the actual image processing pipeline, which we will see later. And when the image has finished processing, we store the actual image, also using the OpenCV APIs. And here, as you can see, we store the image in actually two different formats. The first one being the thumbnail format. Oh, sorry. The first one being the thumbnail format, which is basically the one that you can see here. And this is done in order to prevent the user in order to relieve some stress on the network when an image that is not needed in full resolution actually needs to get passed to the front end. And also the other way we store the image is, of course, in the full resolution of the image. And this is the image that gets displayed here when you tap on the image, and then you can just basically save it. Let's go back. And when the image has been actually stored, the backend communicates two messages. The first one is the communication of the actual progress of the computation. So you take the image ID, and this basically gives you the percentage of the whole computation that has already been performed. And the second message is the communication of the actual image that has been computed. Here, as you can see, we support the send of the image in batches, and this is done in order to relieve some strain to the front end, since everything at any time that a new image gets added, it basically triggers a re-render of the web page. So it is generally speaking advisable to batch the send of the image in order to re-render the page just fewer times. And here in the demo, you have seen the send batch size of just one. So we are re-rendering at each given image, but of course we support arbitrary send batch sizes until the maximum number of allowed photos. So when the image here, this is the last step of the actual backend, the Node.js backend. And now let's take a look of what is the GrCUDA backend in charge of. Well, of course, it starts up by setting up the memory. So we have received the matrix from the OpenCV API, and so we create basically the buffers that needs to be brought to the actual GPU. And for the case of synchronous and asynchronous scheduler, the image gets processed in the pipeline and all the functions in the pipeline are scheduled with respect to their scheduling policy. So synchronous, everything is executed one after the other, and asynchronous, everything is executed in such a way in order to maximize parallelism and minimize the data dependency between kernels. For the case of the native CUDA binary, this is actually really simple. It basically, the whole binary does basically the same exact thing, and the Node.js backend is just in charge of forking a new process that executes the image pipeline with the load of the image and the creation of the process, the image, the application of the filters, and so on and so forth. So let's take a look at actually the juiciest part of this demo, which is the code for the process image function. So here we have that the process image function, as you might recall from before, acts differently depending on the fact that the image is either black and white or a colored image with separate color channels. And the fact of the matter is that the process image function that you can see here, the inner process image function, computes just the whole pipeline for a single channel. So for the case of the black and white image, it's just a matter of fact of using that single channel, and for the case of the of a colored image, it's just a fact of splitting the image into the red, green, and blue channels, and then process them separately. We will take a look at the process image color function just for the sake of simplicity, but as you can see, they all call this inner process image function, which we will see just in a bit. The most interesting thing here is that we take use of the promise API built in Node.js, which allow to actually execute the function that is wrapped inside the promise in an asynchronous manner. So we can just take the results when the computation has appropriately ended. And here you can see that we are waiting for the end of all those three functions that in the case of the synchronous scheduler will execute one after the other. So for the case of the synchronous scheduler, the red channel will always be processed before the green channel, which will always be processed before the blue channel. But for the asynchronous case, we can always overlap channel computation. So this is an interesting thing due to the fact that even if the computation is asynchronous from a Node.js perspective, if for the synchronous scheduler, the computation will always happen synchronously if you're using that kind of scheduler. So let's take a look at the actual process image function, which is in fact actually in charge of the bulk of the computation. And as you can see here, it basically begins by creating the buffer that will hold the image and the temporary images that are created in between, and this we are doing it via the device array API provided by GrCUDA. The device array API is basically a level of abstraction on top of any array, matrix, on tensor that you can think of, and basically encapsulate the fact that everything you can create an array with an arbitrary number of dimensions, either single dimension or two-dimensional or multiple dimension, in the same exact way. As a matter of fact, here we create an array of a single dimension, and here we create an array of 2 dimensions using the same exact API. The other thing that needs to get passed to the device array API is, of course, the C type of the elements that will be stored in the array. So all those basically 20 lines are in charge of creating the buffer that we will use in the computation. And here we can see one of the first interesting thing is that we are copying we are copying a loot table, which is in charge of changing the color in the final image from the Node.js realm to the CUDA realm. So from memory that sits in the host RAM to the memory that sits in the GPU RAM. And the most interesting thing here is that everything happens completely transparently. So you can copy an array that sits in CPU memory to an array that sits in a GPU memory, just using the a normal assignment, and this is due to the fact that you have full interoperability between device array and actual Node.js arrays. So when we have just basically copied everything that's necessary from the host machine to the actual GPU, we can actually start the computation. And as you can see here, let's take as an example this first filter, which is the Gaussian blur kernel, and we create this kernel in this way by using the build kernel API provided by GrCUDA. The build kernel API basically works in this way. It takes as an input a string, which is the actual GPU code of the kernel, and this is just completely normal GPU code as you would have written in C++, so there's no additive overhead of learning a new way to write GPU code. It's basically always the same. It takes the string of the kernel that will be compiled just in time, of course, the name of the kernel, and the type hint for the signature of the function. And those types are, if the types are, let's say, integral types, you can use integers, floats, and as a matter of fact, all the integral types. And if those types are pointer types, you don't need to specify specifically which type of pointer you need. Everything will be handled inside the actual kernel. As a matter of fact, another interesting thing here is that we use the const keyword in order to specify which pointer, or for that matters, which vector does not change during the computation. Of course, everything would work also if we didn't use the const keyword, but this is a hint to the scheduler that all those values contained inside those vectors will not change, and therefore, if there are two kernels, for instance, that use those values as input, the scheduler can, the asynchronous scheduler can schedule them both concurrently without basically having any problem. So we were taking a look at the Gaussian blur kernel, and here you can see let's see this funny syntax on how you actually call the kernel. And as you might see, it's really similar to how you would call a kernel in basic C++. As a matter of fact, as a first argument of the kernel, you have the number of blocks. As a second argument of the kernel, you have the number of threads. And as a third argument of the kernel, you have basically just the number of grids that will be used in this kernel. And this is due to the fact that this is due to the fact that the build kernel API returns an higher order function. So a function that takes some arguments and returns another function. So this first line actually creates the kernel configuration, and this second line here, okay, so basically, maybe it's better to see it in this function, it's more clear. This second line actually calls the kernel. Well, of course, we also support any actual kernel configuration that CUDA supports. So we support multiple dimension block and thread number, as well as single dimension block and thread number. So this is, as you might see, this is all the computations that are done inside the image pipeline. And let me recall you that all those functions are called one after the other in the synchronous scheduler, and they are scheduled asynchronously for the case of the asynchronous scheduler. This everything is just in time scheduled. Here you can see just a little trick which is required in this case. For the case of the asynchronous kernel, of course, the computation would go fine in any case, but we just access a value in GPU memory in order to create a point in which the computation has to stop, and this is done basically just to take the actual execution time of this computation, which otherwise would not be possible since the computation happens asynchronously. After that, we of course save the image in the we of course save the image in the final buffer, and we are in charge of destroying the buffers. Sorry, we're in charge of destroying the buffers that have been used inside the actual CUDA computation. So we have basically reached the end of the things that I wanted to show you about the GrCUDA API, but there's a little thing that I also want to show you, which is related to the fact that to everything that Alberto said. So basically, GrCUDA provides much shorter and more comprehensible code with respect to the full CUDA computation. So here you can see the function that I've just shown you. It's the process image function as we were calling it before in the Node.js realm. And here you can see the same function that does the same exact thing in the C++ implementation. For what regards the allocation of the memory buffer, it's just basically the same, about the same number of code, about the same complexity, with the only difference that here we also create all the streams that will be required in order to actually properly synchronize the different kernels, whereas everything on the other side in the GrCUDA realm is basically just done transparently to the user. For what regards the execution of the actual kernel here, as you've seen before, this is what happens in the GrCUDA realm, and this is what happens in the actual CUDA realm. Here we need to, of course, hint the GPU to actually prefetching the images, whereas this is done completely transparently to you in GrCUDA. And for the case of sync computation, we need to synchronize every kernel after it has been computed. And this is also, of course, a big mess, because you need to remember actually to synchronize with respect to the correct stream each kernel each time. And this is also even more messier for the case of asynchronous computation, because you also have to actually create the asynchronous scheduling inside the you have to actually create an asynchronous scheduler inside the actual C++ API. So you have to attach the streams to the kernel, and you have to create events in order to synchronize the actual kernel inside of the computation in order to make everything work correctly. This is, of course, everything is done completely transparently to you, and of course, in the correct way by the GrCUDA API. So I've finished my short code demonstration, and let's see a brief summary. So in summary, what do we give you? Of course, we give you better productivity because you can write fewer lines of code, but this is which make basically the developer experience much better. But of course, it is not just the developer experience. We also give you better performance. We perform asynchronous scheduling and automatic scheduling. Synchronization, we perform prefetching, and we offer interoperability between different languages which can all access the inner CUDA API. And this all results in the end in this specific setting with a 40% speed up with respect to the basic GrCUDA implementation, of course, by using the asynchronous scheduler. So in the beginning, this is just a few parting words before we left. In the beginning, GrCUDA was born as a project to enable the use of the CUDA API to many different languages. So it was basically just an interoperability layer between different languages. But now, today, we are enabling transparent scheduling, the asynchronous scheduling on a single GPU. So we can also are giving you better performance with the exact same code. And also the performance are comparable to the native C++ API, because of course we don't want to lose performance in going to a different language. And for what's tomorrow for us? Well, of course, we hope that GPUs will become first-class citizen in GraalVM. We are working on multi-GPU transparent scheduling, so the scheduling not only of different kernels on the same GPU in a concurrent manner, but also on multiple GPUs. And we certainly are working also for supporting more libraries and more high-level domain-specific languages. Well, I've reached the end of this presentation. I would like to thank you for your attention. I also to thank Oracle Labs, Oracle Cloud Infrastructure, and Oracle for Research for their enormous support here. Once again, thank you for your attention, and I would love to answer your questions. Okay, I will stop sharing the screen, and let me take a look at the.
Sorry about that. I'm doing the share screen now. Thank you very much, Alberto and Francesco, for providing that really excellent talk. I found it very interesting. I've seen there were quite a few questions. Just let me bring those up. Okay, so I think we've got, always forget to mute that, then okay, there we are. So we had quite a few questions coming up, so I think we'll just go through them in order, if that's okay. So first one, how does the GrCUDA code in process image know which GPU, so which CUDA device ID to target? Because we didn't see that, I think, in the code itself.
Okay, so let me share. Okay, you're sharing this thing, so no problem. Actually, in the beginning of the in the first file that I've shown you for the backend, the basically the main file, which is in charge of creating the actual backend with the WebSocket and the communication with the front end, we use the CUDA set device API in order to set the GPU to which the image processing pipeline needs to work. We also have access to the this specific API inside GrCUDA, and the actual GPU, so the number of GPU that needs to be targeted is passed as a command line argument.
Cool, thank you. Okay, we'll move on to the next one. So what is the cost of just-in-time compiling of the kernels? Can a repeatedly used kernel be pre-compiled once and then used many times?
Okay, I think I can maybe say about that. So the cost of well, compilation is pretty much the cost that you would have even without GrCUDA. So it depends on the that you are compiling, but you can expect anything from like a few hundred milliseconds to half a second or something. Of course, you don't have to compile the kernels directly in your code, but you can do it actually before let's say beginning. You can basically load them as it's called, like yeah, basically it's possible to load them as basically libraries. So yeah, that's also something to basically and okay, say not have this cost of compiling the things, basically. Yeah.
Cool, that makes a lot of sense. Thank you. Okay, so we have another question. So this was, it's really nice to be able to mix CUDA into JavaScript and Python and R at the beginning. What is the time cost of moving data or calling functions between those two languages?
So yeah, that's actually a very, very good question, because it's definitely one of the things that we are trying to improve the most. Because what happens now is that basically if you have like a JS buffer, basically you have to copy the data to a GPU array, and that still takes quite a bit of time. Where to give you an idea of the total processing time, about 20%, 25%, I would say, spent on that. It is definitely something which can be improved, for example, by taking advantage of JIT compilation in GRAL, and yeah, basically that's something which can be improved. But at the moment, you can expect like about this kind of basically time spent on actually a copy between the different languages.
Cool, thank you. That does make a lot of sense. And indeed, actually, I think that follows on to the next question, because I think it was surprising when you showed the results of the JavaScript GrCUDA async that appeared to run more quickly than the native CUDA, which I think was the C++ CUDA code, if I understood that correctly. Was there a lot of speed up that you gained by running those calls asynchronously?
I think that maybe Francesco can tell us more about this.
Of course. So
why it's happening. Yeah.
Okay, so the main thing is that how so there is a lot of overhead basically in spinning up the actual native binary at each time. So in order to make the so let's say in order to make the comparison between the GrCUDA APIs and the native binary, we basically just need to process one image at a time. So one image at a time requires one process to be spawned at every time. So there's basically some overhead which gets lost, some time which gets lost in actually spawning the native binary. In any case, the speed up with respect to native CUDA and the asynchronous scheduler was pretty minuscule, I'd say, within in the margin of hundreds of a second. So this is just to showcase that we have basically the same performance. Of course, there's some overhead involved.
That's good. I think it's impressive actually to be able to have that running from JavaScript. So, I've been doing a lot of JavaScript programming recently through the website and other things, and to be able to hook into having a GPU on the back end for that, I can see could be a very useful thing. So very interesting. Okay, so the last question here is, would it be possible to create a GR OpenCL or similar wherever sort of the non-CUDA GPU accelerated landscape is going? Do you know if anyone is working on sort of linking sort of non-CUDA GPU code to JavaScript, Python, or R?
So yeah, I mean, in principle, yes, it is definitely possible to do it. In practice, CUDA is pretty good because it offers basically this kind of managed memory where you don't have to take care of transferring data between CPU and GPU, which make things basically much better from like the point of view of basically tracking where basically all the different how can I say, basically all the different data are. So yeah, technically it will be possible. It might be a little bit more difficult though, because you have to add all these extra things to track data and yeah. I mean, is anybody working on that? I don't know specifically. There's definitely a lot of work about, you know, like simplifying GPU programming, things like that. So I don't know specifically about OpenCL. I can think of few works which were doing something quite similar. They're not precisely the same thing, but I mean, there's definitely some point in common. So I guess that I could send you some pointers if you just write me message or something. Yeah, so it can just.
I'll get the person to ask the question.
Okay.
Or whoever asked the question, could you send a message and we'll make sure we'll get that information for back to you. Or if Alberto, you send it to me, I'll put it into the Slack channel for SeptembRSE. But thank you. I think Alberto, Francesco, that was a really fantastic talk. Thank you very much for sharing that and also for answering all of the questions. What we're going to be doing now is we're moving to a 5-minute break before we then move on to the next panel session. So once again, thank you, Alberto and Francesco, and we look forward down to the next panel.
Hi, everybody. Good morning. I am so sorry to start slightly late. They are testing the fire alarm in my office right now. So it figures. Hi, everybody. And I just want to say a big, huge welcome to those who are coming here today. I'm going to start about a little short presentation. Okay, play from start, please. There we go. Welcoming all of you guys. Oops. And then, of course, it does that. Welcome you all, guys. I'll just go ahead and just read it from here. No big deal. My name is Kristen Merritt. I am a program manager here at Alice's Flight. And I actually want to welcome you guys today to the RSE and New and Unconventional Technologies panel. And so what we're going to do today is we're going to explore the role of the RSE in HPC, AI, and ML. Now, we're going to actually be doing this with questions via Slido. So as we go through this, if you guys have any questions you'd like to ask our panelists, just go ahead and drop it in there. I believe my fantastic co-volunteer for panels and discussions, and also Christopher Woods, who's been running this whole thing, is currently dropping that link into the chat. So by all means, start asking your questions now. Now, I just want to give you guys a little bit of background and some context, as well as introduce our fantastic panelists to you before we start all the Q&A. So here we go. When I started in HPC about 5 years ago, I went to a bunch of presentations, one of which was given by a early RSE at the University of Sheffield, Mike Croucher, who now works for MATLAB. And he would get in and start talking about what he called the long tail of HPC. And what it was for him was sort of like this pipeline that would kind of bunch up at the end, where you saw the maths, engineering, and physics, basically the founders of HPC and AI and ML kind of coming in and taking a lot of that resource. And behind that, you'd have a lot of upcoming technologies, a lot with drug discovery and life sciences, which actually proved to be quite beneficial during the pandemic. And even behind that, some really interesting stuff happening in the humanities. And really from the beginning, it was a bit of a fight. So because we were dealing with traditional HPC and traditional hardware resources, it was often a kind of a scramble to see who could get a hold of what. And this long tail just would kind of trail off into kind of the eternity, where you kind of would wonder who would finally get to that front of the queue. I'm pleased to say that over the past 5 years that I've been working in HPC, we've seen a real lovely lift of resources, a diversification into public cloud, private cloud. There's services now being offered, as well as like co-location and a bunch of other ideas that are coming along the pipe that are actually making it less about a long tail with a bunch of people bunched up at the end, and more about lifting up these wonderful technologies and these wonderful fields into utilizing HPC, AI, and ML. So my cutesy little introduction is really today to talk about the wonderful people who I have brought together on this panel today. We are talking about people who represent the industry. We've got some scientists on board. We've got wonderful people doing some really cool stuff with fresh insights into how they deal with data. And I'd like to introduce you all to them right now. Well, first on this call, we have Matthew West. He's from the University of Exeter. And Matthew has worked globally. So he's like me. We've got funny accents and live in different countries than we were born in. He is developed a breadth of experience, and he works to utilize scalable computing for researchers to help them solve their problems. From the industry side, we have Darcy Latimer from Red Oak Consulting. And Darcy, he serves as a managing consultant on long-term strategic relationships. And so I've seen him as part of countless HPC programs. And so I'm really glad that he's here today to kind of give us a bit of strategic business insight into what's going on. We also have Andrea Townsend Nicholson from UCL. So Andrea has been on the front lines of projects transitioning into HPC, and she's actually currently facilitating the introduction of personalized medicine into clinical practice. So these are people who have never worked in HPC, and it's a very mythical concept to them. And finally, we have Christina Last. She's a research data scientist at the Alan Turing Institute. And Christina, and I'm not joking, is working on a project that brings together, and this is from their website, historians, data scientists, geographers, computational linguists, and curators all together. And she's going to end our panelist Q&A kind of giving us an overview of how in the world that's coming together, but I'm really excited to hear about our project. And finally, people that you won't be hearing from on the panel, but I just need to say a big, huge thank you to. We've got Will Mayers, who is my colleague at Elsa's Flight. He's going to be the scribe for this. He's in the background, making sure kind of propping me up and making sure that I get all the info. Marion Hardy from Durham University, she may or may not be able to attend. She's actually chairing another session at this time. She actually started me down this path on looking at the way the RSE needs to be brought into HPC, AI, and ML. James Womack, who I've already mentioned, who has been my co-volunteer for discussions and panels, he has also been a huge support. So that's really where I'm going to do my tiny little presentation. I'm going to scroll up to the top so I know all the questions I'm going to ask of everybody on this wonderful panel. I'll stop sharing. And if my fantastic panel can turn on their mics and their videos, I can kick it on underway. And I'd actually, if Darcy's on there, I'd like to start with him if that's possible. Hello.
Hello.
I am so happy to have you on this call today. It has been a big thrill of mine to get some industry insight into how people get into HPC, AI, and ML. So my question that I'd like to ask you is, when you're starting out on the forefront of a new project or you got a new idea, what are the kind of key things that you would love people to sort of have in mind before they go diving in to something this big?
Sure, absolutely. It sort of depends on the context. So we work both in sort of the commercial and industrial sectors and large government, as well as the research context as well. So generally the first thing, because we're external consultants, we're going to talk to you about your governance model and your funding model, just because actually at some point starting a project, you can't finish it. And then we start talking about skill sets. The specific types of support that you might need, whether you've got the organic skills already in your team, or whether you're actually looking to bring those in from collaborators or external companies, and maybe what the training requirements might be. So if you wanted to actually upskill your scientists and your administrators and indeed your RSEs. And then we tend to start talking about the data and the data lifecycle next. It's not so much the computational resource, that's kind of, it's almost a secondary consideration. So we ask you not just what sort, but where it's going to come from, and the rough orders of magnitude in terms of scale that you think you're going to be starting with, and what the trajectory of travel might be in terms of the growth and the size of the data. Do you have any open access requirements? So this is particularly pertinent in the academic sector, where actually an awful lot of the grant money comes with, a long tail of, you have to have this data made publicly available. Who's going to pay for that once the project is passed? So not all universities have an open access research facility that you can actually stick the data in. And actually, how long will you need access to it? Because an awful lot of data, especially when you're generating large training data sets or interesting kind of databases of in silico kind of experimental results, you might actually want to go back to that and do reanalysis again and again. So actually, where is it going to sit? How close to the HPC does it need to be? How easily accessible, that type of thing. And then we tediously talk about things like GDPR and personally identifiable information and the security requirements and all the other bits and pieces. No, not particularly fun, but really important. We tend to talk about platforms and workflows next. So, we talk about, the types of systems you already have access to, whether that's actually appropriate for the context of the research you're doing. We talk about the tools and the libraries and the visualization requirements that you might have, because again, this has a huge impact on how well it will work remotely and, where the data is coming from. We talk about workflow orchestration, and we talk about automation next. So not just the scheduler, but actually the types of things that glue, jobs. Do you actually have a workflow? And this is particularly common in some of the biological sciences and the chemistry and the molecular sciences. That's about, we start to talk about computational needs at this point, so actually, it's long down the list. Computational stuff is almost a solved problem. But again, in an academic context, you probably have free at the point of use requirements, but actually in a commercial setting or in a collaborative setting, you're actually talking about, well, how are you going to fund this? Where is it going to come from? Is it an on-premises solution? Is it a cloud solution? Is it a hybrid solution? So we start talking about the requirements along that point. Do you have sustained computational requirements, or is it quite lumpy? And what would be an appropriate solution for things? We talk about scale. So, strong scaling, weak scaling of your actual application problem, but then actually how much does the, taking a direction of travel, how big do your problem actually become once you've actually got the workflows up and running? And And then we start to talk about things like, well, what's the most important thing to you? Is it the quality of the solution, the time to the solution, or the cost of the solution? And generally you can have two, but not all three of them. So, I mean, that's the primer, that's the starter for 10 when we start talking to people.
So really simple, something you can do in 5 minutes. Easy stuff to work through.
Absolutely.
Yeah.
Generally, it feels quite heavyweight when we start talking about these things, but actually it's time invested up front, like everything, massively reduces the pain at the end of the project.
Oh, I totally agree with that, because from all the experience that I've had, especially with those projects that have transitioned, it's the upfront time. But every time our projects have done that work and put in that work, I think what happens next is it gets easier and easier as you go along. So thank you so much for that, like lightning fast. And I hope some people were frantically taking notes there, because that is some really high level stuff. And I know that it's not what everybody's going to come to the table with. But since you didn't mention resources, I want to talk to Mr. Matthew West about resources. If that's okay, Matthew, on the call? Make sure you're connected. Okay. Hey, Matthew, how are you?
I'm all right.
So it's interesting how I've come to put together this panel. I have actually known Matthew virtually this whole time, and and when we get to the wonderful program at the end, that was actually through the network. So I'm really excited to have Matthew here, because Matthew, you were like me. We've kind of worked all over the place, and one of the things that you always talk to me about is resources and the power of RSEs, with being able to request resources or get resources or have say in the type of resources that are being used on a project. And when you've got people who are chomping at the bit to get to HPC, because I know you're really focused in HPC more than the other two fields. In your experience, do you feel that the RSCs kind of have any kind of power with getting resources, or,
getting resources? Not really. Oftentimes they just say that RSCs exist in the software space, and then you have to go talk to IT or, other aspects of advanced research computing when it comes to, hardware issues. But since there are a number of cases where, we're the first port of call sometimes, where someone goes, hey, I have a project we've been running on a workstation for 2 years. Our data has just scaled up by a factor of 10. We need to find a new solution to do so. So then it's a matter of like, we're the first consultant contact before, and therefore pointing them in a particular direction of, okay, if it's locally, to be like, all right, what do we have here that can help solve your problem? Or do we need to reach out to, external ones, which they might not even be aware of, aspects like the JADE, I think, is the Essex, where there's a particular HPC center primarily focused on biology and ecology work, or is that folks who are familiar with a particular thing just be like, hey, no, you can go apply for time on, Archer 2 or one of the Durham or Dirac machines. Is it they might not even be aware of, particular resources existing. I originally come from astrophysics, so is that when I started, it was we had a local group cluster and existed in a large collaboration where there was just resources available. You'd have to share with other people. But for lots of these smaller groups, it's both a knowledge of what's out there available and also what best fits their particular workflow. As Darcy has already say, is that it might be, maybe you don't need, a particular aspect, because oftentimes they come of like, this is what we have, but people come with preconceived notions of, what's necessary, what they need to do. And it's also just, my personal opinion, I would like to see a little bit more interaction regularly with sort of the hardware and software folks, that it's so we can draw those links together and make sure that everybody is getting resources that best fit their research projects, which is always very tricky.
Yeah, you're not alone on that. I've heard a lot of people say, I wish from a software development we could have more in the hardware, and I think that can sometimes be a bit of a political minefield in some cases. In other cases, I think sometimes people come with more expectations than they have, or they don't have anything to give you, and so you spend a lot of time trying to speak their language and pull that information out so that you know where to point them.
But as Darcy said, is that, and it's those initial conversations of gauging, what do you want to do? Because, I'm coming in from an RSE with a particular background and particular interest, and it'd be like, don't assume, your, computational linguistics, I know what you're talking about. Read me into your project so that I can help you the best way possible. And is the, that's just the way it is. I'll leave it up.
That's okay. Darcy, you want to say something?
No, I wanted to reinforce that point, which is actually what we're really talking about here is signposting. It's signposting to get to the right people in the RSE teams. Sometimes, especially in universities, you're actually talking about like postdoctoral research fellows who have the domain-specific knowledge, who then are the ones who really should be interfacing with the RSE teams, who then have the more generic, how do I size and scale and move this to a more appropriate computational context. So, I mean, we do that. We find that all the time. And actually, universities are peculiarly bad at signposting where help is actually to be found.
And then the other issue of like, what are available resources? And it's just, you get aspects of like, should I always be running in cloud? I always keep hearing people tell me that I'd be running in cloud. Do I have HPC resources locally? Is there something else? I have computing money. Should I buy hardware and like give it to somebody? Can I share it? Is it just mine? It is, oftentimes, when people come with funding, is that there is some, computing component to it. So is that even if we aren't specifically dealing with it, we often act as a go-between between them and other places.
Very good. I actually, I want to bring Andrea in now, because the thing is there's another layer on top of this, and Andrea Townsend Nicholson and I have actually worked on a project around getting a hold of resources. We did cloud because it was pandemic and they needed to float around. Andrea, are you on?
Yep, I'm on.
Oh, fabulous. Hello.
Hello.
And yeah, our lives have been virtual as well. Andrea comes at this from a really interesting angle because she has been working very, very hard in transitioning people into HPC. And these are fields that up until recently, that's just been a box in the corner that blinks at them. And now they're really kind of moving into learning and being educated on what HPC can do and the potential for them in the real world working in clinics. So Andrea, can you tell us a little bit about that education side and being able to train people once they come in and want to get to know more?
So I suppose for context, I should say that I have, over the past 20 years, been waiting for the compute to get to the level where the computational methodologies converge with the experimental findings. And there have been a whole bunch of reasons why that might not be possible. Some people, like my research group and others, work on proteins that are embedded in membranes. It's been hard to get the structures for them, so hard to get the data. But we spent a lot of time watching and waiting for everything to come to the right point, only to discover that it was in a different field, tuned in a different way, with other people using it, without a culture and practice. So like Matthew said, we have very much a similar experience to astrophysics, maybe about 15 years ago, where you would want to repeat your computational experiments. So we do ensemble-based things. So the compute expands even more, and you have all of these things that come in, and then you find that you need to start somewhere, and you need to start training people in this. So we made a distinction between training and education. And training is obviously for people who would be more in the postdoctoral phase, maybe as postgraduates, early career researchers, or somebody like me who needs to upskill in a screeching hurry. So that's always fun. But education, we thought the best thing to do would be to start and embed things in the university curriculum. Once it's in a university curriculum, it's pretty much in there for decades, easily decades. So it's an excellent way to create a culture and a practice. And so I started embedding it in medical students courses. They take a course that is free for them to choose in their area of interests. And we started focusing on this idea of how you could use computationally informed digital avatars as part of your clinical practice and decision making, and where you put a stent and how you do these variety of different sorts of things. And we had to start from first principles. They'd never used the command line. That was fun. There were all sorts of bits and pieces around learning a new practice. And at each step of the way, we've sort of said, well, what did you really like? What did you find that was difficult, and how could we make it easier? And the things that were found to be difficult, which is familiarization with remote systems and headless systems and things like that, really, they could come up with no way it could have been easier. And it's just one of those things you have to get to terms with. It's like learning a language. You get enough words and then you sort of work on fluency. So it's been a really fun trajectory. It's embedded in our bioscience courses. We've been using significant resource because we had access to it from the European grant that we were funded by. So we've been sitting on PRACE machines in Spain, in the Netherlands, up in Edinburgh at the EPCC. And students love this idea and just have a huge appetite for more. And I suppose, just to draw things full circle, we realized that it was a good approach and we'd been successful when one of our third-year bioscience students who had gone on to do a PhD in a different university contacted EPCC and asked if he could have his Cirrus account back because he wanted to do some MD simulations. And then that conversation started about how you get resource and where these things come from and what's the right machine. But he went to something he was familiar with and asked for continued access to it because he wanted to use it for something different. And I figured that was a win.
Definitely. I think the one thing that my experience with you on the projects was how once you could get people familiarized, their appetite just would grow into what could potentially happen. And not only that, that's great because you want that kind of inspiration as we move into even bigger technologies. And I'm sure at some point in the panel, the exascale question will be asked. So you need to be ready.
So I'm not as interested in what I try to train or educate people to do and use. I really want to see what they'll do with it after it becomes native for them and what happens when it's just part of their normal practice, because my view is constrained. It's something I came to. It's not something that's just always been there. I'd really like to see what the next generation does with these things and the uses they make of them. So we're trying to ask as we go along, you know, what in your personal life would you want to do on HPC? What sorts of things would you scale? Can you see, I don't know, organizing collections and things? What would you use it for?
No, that's fine. And actually, you really found a wonderful way to segue into Christina, who is working on something absolutely mind-blowing crazy. Christina, are you able to join up? Make sure you're connected. Hello. Now, Christina has come to this panel through the wildest ride I've ever been on in my life. I started to work on a project for the Supercomputing Conference on looking at how HPC is being utilized in humanities. And through that, I got connected to all wonderful people. And they kept saying, living with machines. You need to talk to Alan Turing. You need to talk to living with machines. You need to talk to that group of people. They're doing some really cool stuff. And I believe you prepared a few slides and things. Yep, absolutely. Christina is going to talk to us about some of this wonderful next generation stuff that's on the map and give you kind of an idea of the sort of things people are looking at doing and are doing really right now on with HPC, AI, and ML. So in humanities of all places. Take it away.
All right, perfect. Yeah, let me know if you guys can see the screen. So I'll talk about the Living with Machines project. It's projects in collaboration with the British Library and the Alan Turing Institute. And I'll specifically try and kind of focus the discussion around how we're using cloud resources to scale some of the analysis that we're doing. But I'll give you a bit of a background on the team and also the project itself, just so you guys get a baseline for this. So about who is working in from the Alan Turing Institute on this project. So I'm a member of the research engineering group there. What we do is we are basically found from the idea that we want to be able to create this kind of research software engineering skill set and research data science skill set to partner with universities and other collaborators as we've expanded more recently. And basically, we want to help them scale up some of the open science and academic research that they're doing. And this is basically how the project with the British Library started. We're a growing team of 33 people from all walks of life. My background is geography, but we have also computational linguistics, astrophysics grads, all the way to biochemists as well in the team. And they all came to this idea of research software engineering from these domain disciplines. So it's really interesting to see that also act as an experimental field in itself. And so I'll talk a little bit about the project. So how did the Living with Machines project start? It was a conversation at first between the British Library and the Alan Turing Institute. We are based at the British Library, so there's a clear opportunity there when we were in person for a co-location and kind of having a mutually beneficial collaboration because of this. We basically wanted to look at how did cultural heritage and historical information from the long 19th century impact our kind of lives today, and what can we actually reveal from using data science and artificial intelligence techniques on some of these all historic digitized collections that the British Library has. To give a little bit more detail, the project is basically looking at the human social cultural consequences of the machine age. So this is the period from the late 18th century up into the early 20th century. And this was looking at using kind of computational techniques to analyze historical texts and as well as historical maps, and also developing kind of innovative computational models to be able to transfer this research to other humanities projects. And so the idea is that it's embedded in this radical collaboration between, from all the way to historians of kind of 19th century texts to research software engineers and cloud computing specialists. So the team is big. I'm the newest member. And as you can see here, like these are the range of people working on it. We have software engineers, we have librarians, and all the in-between. So I'll talk about the data a little bit now, because this is where we get into the crunch of, what kind of cloud resource are we needing for the projects, and actually what does that workflow look like? Like Darcy said earlier, the cloud resource and the scaling comes at the end, and you have to iron out all of the creases in your pipeline before you actually get to this point. So for us, we have a large amount of newspapers, 25 terabytes of newspapers. These are all digitized, and there is a continuing effort from the British Library to feed in some of the standards that we describe back to the continuing digitization process as well. We have a large amount of books. These are from the 18th and 19th century, and on both of these resources, the process has been to segment some of these texts and perform OCR on them. So that is extracting the language from the text itself. And we also have the National Library of Scotland, which is a large body of Ordnance Survey maps. And this is basically what we've been using to identify different types of geographic features that have not been kept on in the Ordnance Survey maps from today. And then we've actually lost the understanding of, where were these geospatial, what was happening in certain geospatial locations. And we've been particularly focused around commercial hubs and also railways that have disappeared from the long 19th century. And then we're also looking at census microdata. So these are actual individual records of family households from the 18th century, and looking at how occupational changes happened within, the coming of the machine age, and how did people get automated from, the coming of looms and hand weaving, changing onto the looms, and specifically this case study we've been looking around. And this information is microdata. So actually, I'll talk a little bit about how our cloud resource also integrated with this thing called research safe havens, where we have individual level data or copyrighted data that actually needs to be stored in a safe research space. So yeah, the challenges are here, and we've had a lot of challenges on such an experimental project. Actually talking to a lot of my collaborators from the research engineering group, they've really alluded to a lot of the challenges being this kind of iterative feedback process between the historians, so the non-technical people on the team, and then our scaling of the actual computational methods that we want to do to extract some of this information. So I'll talk a little bit about this, but we'll definitely revisit it in the Q&A from the audience. But basically, batch data delivery, this is nothing to do with cloud, but the fact that we had data from the digitization process coming in large chunks meant that we didn't have a complete set to work with at the beginning. And actually, when we wanted to understand, how much cloud resources we're going to need for the project, so this is even before project conception, having this batch data delivery really didn't help us able to plan the cloud resources that we needed for the project. And so when you're dealing with data that is not a flow, it's not automated through some API, it is literally being scanned in from degrading texts from the 18th century or 19th century, you really have to work on a different kind of scheduling for that data acquisition. There was also the fact that we had too much data coming in. The British Library have all of the newspapers from the long 19th century. And we actually wanted to prioritize whether our cloud resources were going to be used on storage of this data or on compute. And we prioritized compute on the project because we wanted to actually use a smaller subset of this information to extract as much information from as possible to be able to glean some research and understanding from this. So that was a decision that we had to make, and we would have kind of quadrupled our cloud resource cost because of storage for the whole data set. And then it was, okay, so if we're going to store only a subset of it, what do we actually want to store, and how do we have that conversation with the historians and the non-technical experts on the team? And there was obviously some discrepancy about that because we wanted to be able to store high quality information, but we also found that some of the high quality newspapers, they were representing certain political spheres. So a lot of the higher quality newspapers were actually conservative newspapers, and the historians wanted much more spread of political spectrum within the newspapers. So that was a really, really interesting finding that actually kind of diverged the groups. The research engineers wanted high quality for OCR text extraction, and the historians wanted that plethora of different political viewpoints. And then I'll talk about the working in safe havens just a little bit before we go to the audience. But a lot of our work has been on documents that are past 1920, so they're still under copyright, and we've actually had to use them in a safe haven. These are research environments that are high security, and they only allow a small amount of permission issues or permissions, and also there is a large limitation on the types of programs that you can use in these environments. So to deal with this kind of very restricted research environment, as well as such an experimental research field, we had to take small subsets of the data, perform analysis on them, and really kind of shave off anything that the historians or the other researchers on the team didn't find useful, and also assimilate what we would use in the kind of data pipeline or the processing pipeline with what matched within a research environment, a safe haven. And so there was this matching process that went on how we could use certain programs, certain softwares that would be safe inside the research safe haven, as well as what actually enabled the right outcomes to happen with the historians, and that they felt good about the results of this. I'll talk a little bit more if people are interested in the intersection of cloud and safe haven, but I'll move on from now.
That's fine, Christina. So I've just been told that we've actually been having such a good time talking that there is literally piles of questions actually showing up in the Q&A, which is actually great. It means that as you're going, everybody's like, that's so cool. And all of a sudden I see a Slido question pop up. Here's the fun part. I don't actually know how to operate Slido, Christopher. So I don't know. There's the magic thing. So I really appreciate the fact that you were able to talk. And let me tell you, every time everyone talks about living with machines, they tell me this is a fascinating project. It covers so many wonderful areas. And that I was very interested in learning about people who were looking at data historically, not just this is this data. It's like, well, why'd you collect that data? Where'd that come from? What was happening at the time? And I thought that was just a really interesting way to look at how we know what we know, or what we know about that. So let's get on to the questions. It seems the most popular one is actually a devil's advocate question. And I'll actually throw this up to the group. So, you know, we've been talking about transitioning people. Has anybody been in an experience where they've actually told people, not yet, back down, get some more stuff, come back to me? Oh, I see little thoughtful faces. Darcy, do you want to come in?
Well, I'll take that. So it is true that some people do follow the shiny path. So like everybody's talking about AI and ML and stuff, and actually you have to gently point out that they have to walk before they can run sometimes. That's certainly true. And it's not to basically try and follow the buzzword du jour. It's but basically get really good infrastructure in place, get good training in place, get good people in place. You can always move your research and move the tools that you're using along with those people. So that's generally how we phrase it.
Yeah, I understand, because sometimes I think you do get attracted to the shiny objects, and people really want to have something as part of it. And having honest conversations about how ready someone is, I think, is really important. And also, just looking at like Christina's work, looking at Andrea talking about how she was waiting for 20 years for something to happen, and you know, it's like sometimes you got to be a little bit patient for that to take place. So
there's another side to it too, Kristen, and I think that anybody who has been involved in managing an HPC environment for users will be familiar with this, where you have somebody who's come out of a group that's used something successfully before. They have the template, they've been told to go off and do it, but they don't have the understanding of where the data came from. They don't have enough knowledge to realize that they're going to need to adapt the thing for their own purposes, put their folders in their own places, create their own directories, create their own structures, make their own paths. And so a lot of our facility people spend most of their time doing basic training, trying to crank a user on who's just sort of been pushed at something. And that's a really good time to have good training pathways in place, when you can just say to somebody, you know, yep, that's great. That's a great project. Let's just have a bit of a talk about that. And what are you going to do and how are you going to do it? And then see what the need is. I would love to see some kind of a driving test so that you could know where you put somebody at each step of the way, from the desktop or their phone all the way up to an exascale machine, and when they would be allowed onto a system because they'd have enough background for it, and where you could point them to be trained to get that if they don't.
I think Archer might actually have something equivalent to that, if I remember.
Yeah, it does have a driving test, but it doesn't deal with the pre-HPC end of things. And that's usually kind of where you have the problem, at least for a nascent community.
I can speak at least really quickly, is that on a project I'm helping with regards to biological imaging, there was an aspect of like how to identify cells. And is that I spent some time going, yeah, is it, you know, it'd be really nice to be able to automate this and, you know, particular aspects. And then I went, humans are going to be watching this anyways. And, you know, let's just leverage the knowledge in meat space and have people draw circles on an image. And is that, yeah, it's an excess interaction. It would be nice to automate it fully, but the amount of time that would be necessary to, you know, set up, debug, and make sure that it works as efficiently is probably not worth it. And just to use existing workflows that researchers know and are familiar with. So you know, while automation is really cool, sometimes maybe leverage the existing knowledge instead, or simpler methods like draw a circle.
Well, as long as people learn at the end of this session, please do not run your job on your login node. I think we're going to be doing really well.
Thank you.
So as I'm looking, James asked 2 questions, but underneath that, Darcy, it sounds like you are very popular with your written list.
I will happily contribute that. I will send it over after the event.
Okay, and we'll put it up in the what do you call it? There's a little Google Drive folder and stuff like that. We can do that after the fact. So thank you. Yeah. By the way, you literally rattled it down so fast that I'm sure people were like, oh, that part's important. That part's important.
So that was my condensed list. I have a much longer started for 10.
That's true. Okay, what's the next question? We've got public HPC facilities today seem to target traditional HPC workloads. Are these the right tools for emerging fields? Does HPC itself needs to change? Now that's an interesting way to look at things. Now I'm gonna actually point at Christina, because you kind of are in this place where you're dealing with, I think you really are kind of dealing with like that traditional and like trying to pivot it into looking at something, huge amount of documents. So do you have any opinions about what HPC needs to do?
Yeah, I mean, I think, so we're not using public HPC at all, but I think that with the Azure cloud resources, it's not been easy to get non-technical users to understand why it's essential and how to use it. So, just for the starts, that the UI is incredibly confusing. We actually built a tool internally to help people, tear down and create resources in a much more kind of, the standards are a lot better, the security is a lot better than the defaults. And that should be something that should be freely accessible for less technical users in the team. I think for us, we had the flexibility at least to be able to build a cloud resource pipeline that allowed us to scale like a computational virtual machine for all of the processing, especially with the maps analysis. So that was looking and tagging some of those areas where we could see commercial and rail spaces within some of the 19th century maps. And we actually could scale the compute VM on that, but also have a separate VM for annotation. So much like Matthew was saying, keep it simple when you're dealing with less technical users, and also data labelers from the historian side. We had an annotation VM that really only showed the barest minimum for them to be able to execute the tasks. And that it was able to feed into a larger VM that was scalable. And that actually really worked well. We didn't have too many issues on the cloud side with that, but that was because the data was slightly smaller than our newspaper data set. So these were the 2 main data sets we were working with. And the task was kind of well defined at a high level. The annotations were not, but we were able to embed this flexibility into our VM that just helps the annotation team to separate out the labels. They could label them very easily with this just kind of squares and clicking on the locations for the rail space and commercials buildings. We were able to hide a good amount of detail, and I think only showing what's relevant sometimes is a lot better. And then that gives a flexibility for a less technical user to come and actually make use of a pipeline that we've built using our resources. So for us, it's been okay, but the underlying layout and GUI, at least for the Azure, is not helpful for less technical users.
That's true. You do have quite the mix of users. And then to kind of to talk about the next question, James put underneath is kind of related, is learning from each other. Andrea, one of the things that I've noticed with the Comp Biomed Center of Research is that you spend a lot of time trying to get people to talk to each other about your experiences and sharing that kind of knowledge. What kind of things do you think, being a person who has been waiting and now is in, that the traditional methods can learn from experimental science, such as the work you're doing?
Well, part of the reason for talking is sort of to share best practice and see what people are tackling, and also just in our particular area, there aren't a lot of codes that are up and being used yet. And so some of them aren't being created. Some of them are being ported up from things at our desktop. That's what we've been using for our training. And it's just this idea of being able to find out more about what's out there, what people would want. The nice thing about expanding your training to other universities and to other countries is that you can start scoping and surfacing things. So we bring things into our training program that we found in other places. But there is an interesting aspect that we encountered for people who were working in HPC and biomolecular simulations, for example, but came at it more from a physical sciences background than a biological sciences background. And we found that we were doing things differently as biologists. If you ran a simulation or if you ran a calculation to take a look at a protein to work out an interaction that gave you a binding for energy or some kind of a parameter, there was an output number that was calculated at the end of it. But we discovered there were these massive trajectories and frame sampling and everything else. And when we started visualizing within the frames, we could see transition states, or we think we can see transition states in proteins. We can see things that we cannot capture experimentally, but we now have a better handle on interrogating. And so it may be that the way that somebody in the discipline experimentally or clinically looks at something will add an additional layer that can be incorporated in the compute that's done or in the way that things are visualized from the compute.
Thank you for that. Underneath this, there's kind of a bit of two questions that sort of could be merged together. Just it's really about the facilities, standardization, cloud, multi-platform. Actually, I'm going to put this one at Darcy because you have worked on all the platform.
We have.
What do you feel? Yeah, and not only that, I'm going to also ask Matthew about standardization because I think he'd have some interesting views too. But I'm going to start with Darcy first. Is really like standardized facilities, cloud. You know, what is your opinion on all these wonderful platforms?
So at first blush, it seems like there's an awful lot of difference between them, especially between the cloud vendors. They all have their pet ways of orchestration, but in reality, they're just a convenience function there to get you to the scheduler, to get you to use some of the other services, especially the software as a service and platform as a service. Generally, there's a tax for kind of doing sort of platform agnostic work, and you always have to ask yourself is, do I really expect to have to switch horses midstream? And if you do, and if there's a good case for doing that, then you invest the effort and invest the training and the complexity. But in reality, we all know we carry a load of technical debt. And actually, I think it's as much about addressing the technical debt and not using schedulers that are maybe, you know, not quite as technically advanced as some of the newer ones, especially the free open source ones that are coming along, but also not jumping at the first shiny thing. And there's a when you decide to use national local facilities is something I'd really like to address as well, because that kind of has an interesting tie into that, which is we talk an awful lot about hybrid clouds, and actually the concept is lovely, but in practice it's quite difficult to actually do unless you have one of the more modern orchestration tools and stuff. And you know what, most universities, there's like a free at the point of use on-prem kind of solution, then you go to the national tier 2 shared infrastructure, things like Bead and Jade and everything else, and then you start to go to the tier 1 kind of Archer scale, and then you actually have to consider, if you go to cloud, the funding model is different because it's no longer free at the point of use unless your university is actually providing that small scale research facility. So you actually have to think about this funding kind of gap quite early on, and forget the aggressive marketing. It's more about how are you actually going to structure a longer term engagement, and HPC at university level, it's like to support nascent researchers, early stage researchers, to get unfunded research onto the conveyor belts going through the various different stages. And it's all about writing sensible business cases, writing sensible grant proposals, and actually having a longer term view about, I'm starting here, but I want to get there.
Absolutely. So Matthew, you've been doing some wonderful work dropping in links and things into how people are being educated. So we'll just kind of talk, we'll kind of like look at the culture of questions that are still left and really ask about like really educating people as well as looking at the right type of platform for them. What were your thoughts on this?
So is that, you know, I think there's oftentimes certain ones, particularly from it's certain disciplines where like, oh yeah, we're writing Fortran code. You know, I'm reworking my advisor's Fortran 77 code in order to improve its overall efficiency. Is that some of that exists in, you know, nominal HPC spaces, but is that think of researchers who are doing primarily their work in R in small data sets on their desktop, is to be like, you know, do I have to rewrite all of my stuff in a new language with all of these additional tools in order to be, you know, doing proper HPC work? And like my generic answer is no, but is that it does matter of like, you know, where you want to run. And, you know, with certain facilities might say, no, that's not well fit for our resources. And is that I think it is, you know, very useful for folks to be like, all right, finding fits. There are lots of different ways to do big scalable computing work. And it's also that you can start doing big scalable computing work without having to completely reinvent the wheel. If you have existing software, we can help find a place for you to run that, you know, larger. You may need to make code changes, but it's not as if you now need to become an expert in C++ in order to make everything work. You know,
Andrea has
I
a thought
promise
on
you
this.
that's not necessary.
Andrea, your thoughts on this as we come
I
to the
was
end.
just going to say that there's a really interesting question about efficiencies within a discipline and things that you bring onto HPC, and scaling happens outside of the compute environment as well. So for example, in the biological sciences, a lot of things that were done manually in small numbers now have been scaled up. Our DNA sequencing is scaled. We have all the omics that are generating these huge panels of data come with scale. And there's something that is worth considering when people are looking at what they want to do. And that's what scale should you be doing it at? What do you want to get out of it? What do you get back from it? So like Matthew's saying, if you are seeing step changes and you can see value add, you might put yourself onto a platform technology, and then you leverage the data from that onto a correspondingly large amount of compute. But that's a really big step jump for somebody who learned the single sorts of things. So there's as much in the ethos or the logic of how you construct this is really experimental design or research design, every bit as much of it as it is resource design. So yeah, you might not need to go into something bigger, but actually you could move your whole platform in your own ecosystem, experimental ecosystem, onto something bigger, and then you would need it.
So we're now in the last 2 minutes, believe it or not. I have been so absolutely grateful for this panel. I love the fact that everyone here came with different experiences, but also shared experiences, even if they're in a different location. So after this event, and I've just dropped it in the chat, UCL is actually going to continue this conversation. So if you're actually interested in getting something very specific, it will be specific to the university, but really want to hear more from people who are dealing with this kind of transition and where people are and what people are after, please go ahead and follow that link, and you can go do that during your lunchtime. Some of the panelists will be available for that time. Again, I really want to say a massive thank you to my panelists, to everyone who joined, the fact that we had a ton of questions. So there'll be more coming your way in our folder after the panel wraps up. So thank you guys so much.
Thank you all.
Glad to be here.
Thanks, guys.
Absolute pleasure. See you, Kristen.
See you guys soon.
Thank you. Bye.